Okay, so this is part 3 of lecture 1. So let me share the screen. Okay. So at the end of the last part, I asked you what you think. Do you think that POR follows from some rules of logic? And the answer is no. This is simply an observation about how our universe behaves. Experiments show that principle of relativity holds. And it has basically been lifted to the status of a postulate. It's basically an assumption. Okay, so it's not provable. It's just basically an assumption, or as Einstein has done, he just simply lifted it to the level, to the status of a postulate. So principle of relativity is assumed to be true. It's like a super law. In any case, if QR seems so obvious, what's the big brouhaha? Why am I making such a big deal about it? Well, recall the statement that all laws of nature must take the same form in any inertial reference frame. If you think about it, what it really implies is that POR actually puts a constraint on the kinds of laws that can exist in nature. It acts like a filter. You give me a potential law of nature, I have to test whether it is consistent with POR. And if it isn't, I have to rule it out. Okay? It's like a test for whether a rule that you come up with, a law of nature that you come up with, whether it's legit or not. And if it's not, we simply reject it. So POR eliminates lots of candidate laws. Okay? It's like a super law. So here's a quick homemade example, and then we'll make things more serious. Let's say you have a roommate that's taking Physics 141, and they just learned that a law of friction. It says, here's a law of friction. A brick in contact with the floor comes to rest, or mathematically, velocity of the brick goes to 0. So here's example of using POR to test legitimacy of laws. Example, candidate law. A brick in contact with a surface must come to rest, or the brick goes to 0. Now I want to ask you, is this a legit law or not? Is there anything wrong with the statement? A brick in contact with the floor comes to rest, or velocity of the brick goes to 0. This seems pretty kosher, but there's a problem here. Okay, so what is the problem? This is indeed wrong. Okay, now we have to eliminate this. Why? What's wrong with this? This seems like a pretty good law. What's the problem? Well, if we think about it, this does not obey principle of relativity, because while in one frame, the speed does end up being 0, in the lab frame, in the frame of the table or of the floor. In another frame, it doesn't. So if an observer on the train observes the experiment, he or she sees that the brick is changing velocity, and eventually, well, when the brick comes to rest with respect to the table, it ends up moving uniformly as seen from the train. The whole world moves uniformly as seen from the train. So this statement, we all know what student is trying to say. This statement is wrong. So how would we fix it? Correct version. How would you fix it? What would you say? A correct version is this. A brick in contact with the floor or another surface. That's not that important. What's important is that comes to rest relative to it, or to that surface. That's the key. Or mathematically, we would say that the V brick minus V of the surface goes to 0. Okay, we discussed that POR requires the form of laws to be frame independent. And notice, if this is true in one frame, it will also be true in another frame. Okay, we will discuss velocity transformations in a minute, but you can probably see why that is. So if you change to another reference frame, say from the frame of the lab to the frame of the train, you add the same velocity to both the brick and the surface so that the difference remains 0. The difference remains 0. Okay? So the form is now preserved with respect to the reference frame change. Okay? This form remains invariant with respect to a reference frame change. Okay? This form also does not depend on the orientation of coordinate axes, by the way. I said nothing about coordinates. I didn't even say whether it's in 2D or 3D. And this is a little bit of a more advanced statement. Maybe those of you who are physics majors might find this interesting. Is that what makes it coordinate or frame independent is the fact that it relates to geometric quantities. Vectors are geometric quantities, they're arrows. Okay? So that makes it frame independent or coordinate independent. Okay, so now I would like to give a couple more serious examples in which we take a potential law of nature and we test its invariance with respect to a reference frame change, and you will do some more in the homework. And along the way, we will see that the classical physics that you know from Phys 1 is actually the simplest set of laws that are consistent with principle of relativity. But in order to do that, in order to look at more serious examples, not a kitchen-made example like this, in order to do that, we need to learn how to transform from one coordinate system to another. So that's our next point, called coordinate transformations. So we're going to make precise the idea of relating something into different frames and develop a mathematical tool for that. So here is a coordinate system S. Okay, so this is frame S with its coordinates. And here is frame S prime with its coordinate axes, which I call its prime y prime. And let's say this frame is moving with velocity v, okay? So this is, so frame S prime is moving relative to frame S with velocity v, okay? It will be a convention that, so this is a convention, we will use it very often, that the origins coincide at time t equals 0. In fact, that's a definition of t equals 0. So let's say you have a car and a train, and you put the coordinate system of each object at the back of each object. Okay, so you put, let's say if this is, if S is a frame of a train, and S prime is a frame of a car is bypassing the train, it's outrunning the train. And I put this coordinate system at the back of the train, and I put this coordinate system at the back of the car. As the car is passing the train, at the moment when the back of the car passes the back of the train, I start the timer. Click, t equals 0. So that's a very common scenario. It's not really necessary, but it's very helpful to make things concrete when we do calculations that relate things from one frame to another. Okay? All right. So so now let's say an event took place at some later time, not t equals 0, but some later time. What's an example of an event? Let's say you're on the train with your coordinate system, and passenger has just crossed from car 2 to car 1. Boom, that's an event. It took place at some place on the train. It took place at some time. And so you can also ask, well, what's the coordinate? What's the coordinate of that event as seen from the ground? Okay, that's a legit event. But let's say something picturesque, something clear, like a firecracker exploded. Okay, so t equals at some time, boom. Okay, firecracker exploded. Okay, and let's say in frame S prime, this took place at position X prime. Okay, I already labeled the axis X prime, but you know what I mean. For example, 3 meters. X prime could be 3 meters. So this distance right here is X prime. 3 meters from the origin of frame S prime. That's what this means. What is the coordinate of that event in frame X? Well, this distance right here, remember at t equals 0, the origins coincided, time t passed. So this is time t. The explosion took place at time t. At the point when the explosion took place, at time t, not t equals 0, this origin has moved the distance vt. Okay, because this is moving with speed v. Therefore, altogether, x, the distance from at the origin of S equals x prime, this little bit, plus this bit. And that's it, really. This is an example of a coordinate transformation. Okay, so x equals x prime plus vt. So this is example of a coordinate transformation. It sounds more fancy than it really is. Okay, this is coordinate in S. This is coordinate in S prime. A transformation in general, coordinate transformation, relates coordinates in two frames. Okay? Relates coordinates and times also, but in this case, we're assuming time is universal everywhere. Coordinates in two frames. We will talk about time later. For now, this is the obvious thing. I'm trying to make it very straightforward. So the unprimed position is measured in coordinate x, s, and the prime position is measured in coordinate s prime. So these are the rules for how to relate positions from one frame to another. Now, up until special relativity, up until early 20th century and Einstein, no one bothered to give this a name. It was the transformation. What else could it possibly be? It turns out that this thing is wrong. It turns out that this relationship is actually, it has a flaw in it. Okay? You're welcome to think about why, what's flawed about it. Seems pretty obvious. I mean, we're just adding these two things right here. But it has a flaw. Long story short, people came up with a better transformation that's believed to be perfect, at least right now. So someone had to give this a name to juxtapose to the correct one. The correct one is now called Lorentz transformation. We'll discuss it later. So this one became known as a Galilean transformation. Okay, again, it sounds like more fancy than it really is, and certainly Galileo didn't call it that way. But this is called now Galilean. I'm not sure if I'm spelling it right. Transformation. Okay. In other words, the idea is that there are many kinds of transformations. Another example of a transformation is transformation under rotation. You can have one coordinate system, and in that coordinate system, a point has coordinates x and y, and another coordinate system that's rotated. And in that rotated coordinate system, a point will have different values of coordinates. And you could relate the coordinates in this frame and the rotated frame. My point is, coordinate transformations are very common, okay? This is a particular coordinate transformation for this one, is a particular coordinate transformation that occurs in this context of co-moving frames. And up until early 20th century, it was assumed to be the coordinate transformation for this particular situation. And then people realized that it's not. And so it became known as a Galilean transformation. In order to distinguish it from the correct one, it became known as Lorentz transformation. I'm not going to write it down because we'll get to it. We'll cross that bridge in due time. So that's transformation of coordinates in this particular setting of two co-moving frames. Okay. What about velocities? How do velocities transform? Let's say you have, again, you have two frames. Oops. Sorry, you have two frames. A second, let me undo this. Okay, so let's say you have two frames. Should I can even, no, this is too busy. Let me draw it from scratch. We have your two frames, S and S prime. It's moving. And meteor comes across, glides across the sky. Okay. Clearly, the velocity as seen from a moving train will be different than the velocity of the same meteor as seen from the ground. In fact, if the train is moving as fast as the meteor, then the meteor will look like it's standing still relative to the train. Okay. So at some point, t, there's a meteor right here. I want to know it's how the velocity in the two frames relate. Well, let's say you were good at calculus, but really bad at physics. What would you do? You would just take the derivative, because that's how you get velocity, right? So you would say, dx dt equals dx prime dt plus the time derivative of dt. And therefore, you would say u, velocity relative to frame s, equals u prime plus v. Okay? This is velocity in frame s. This is velocity in frame s prime. And this is, you already know, velocity of s prime relative to s. Right, so at this point right here, the meteor has a certain velocity vector. And the magnitude of that velocity vector is different in the two frames. Now, I guess this is called a Galilean velocity transformation, right? So this is called a Galilean coordinate transformation, and we may call this Galilean velocity transformation. Right? So this is called Galilean. Okay. Again, it sounds like we're making things too big a deal. It's nothing out of the ordinary. Okay, it totally conforms to our experience that if you're riding on a train that's moving at 45 miles per hour and you kick a soccer ball at 5 miles per hour in the same direction as the train is moving, then the person on the ground will measure the speed of the soccer ball relative to them to be 50 miles per hour. If you kick a soccer ball backwards at 45 miles per hour, while the train is moving at 45 miles per hour in the opposite direction, then the person on the ground will see the ball drop dead. And in fact, I will send you a link to a video from Mythbusters where they did exactly that. It's hard, we all believe it, but it's really cool when you actually see it. Okay, so I will send that link. Or in the case of a passenger tracking through the train, u prime would be the speed of the passenger walking in between train cars as measured from the frame attached to the train, and u would be the speed of the passenger as measured from the frame attached to the ground. Okay, and you can change in time. The passenger doesn't have to walk at fixed speed, just like the meteor doesn't. This is a speed at some particular time. This is a relationship at some time t. Okay, a v is fixed, or I guess v doesn't have to be fixed either, but usually v is fixed. And you're applying the velocity change rule at that one particular time, corresponding to any one particular event, like passenger just entered the car. Anyway, you've seen this formula many times, but you probably didn't think about events. You probably didn't think of this as applying to events. We will talk a lot about relating coordinates and times of events in different frames. Okay. So I already said that nowadays this is known as a Galilean transformation to juxtapose to the correct one. That's called the Lorentz transformation. And I invite you to think, well, what could possibly be incorrect about this transformation? I mean, this seems obvious. And calculus is hopefully the right thing, otherwise they wouldn't teach it to you. So you apply calculus, you apply the derivatives, and you get this. So where is the, in other words, is there some kind of an assumption that we're sneaking in here, sneaking in inadvertently, that makes this wrong? So you think about that. And in the meantime, this is the end of lecture 1. Okay, see you later.